What if I told you that every color you see, every sparkle on a dewdrop, and every flicker of your phone screen is driven by the same fundamental phenomenon? That invisible force is light, and it is far stranger and more powerful than you might imagine. Light is the name we give to electromagnetic radiation that your eyes can detect. It travels at the cosmic speed limit, exactly 2,99,792 km per second in a vacuum. Yet it carries no rest mass. Instead, light is composed of discrete packets of energy called photons. Each photon acts like a tiny messenger, conveying information about its source, its energy, and even the passage of time itself. Centuries ago, scientists argued whether light was a wave or a particle. Today we understand that it is both, that it exhibits a dual nature. As a wave, light can bend around obstacles, spread through narrow slits, and interfere with itself to produce colorful patterns. As a particle, light can collide with electrons, knock them out of atoms, and transfer quantized energy in precise amounts. This wave-particle duality is not just a curiosity. It underpins the entire field of quantum mechanics. When light encounters matter, it can be reflected, refracted, absorbed, or scattered. Reflection sends photon bouncing off a surface, giving us sharp images in mirrors and the sheen on a polished car. Refraction bends photon as they pass between materials of different densities, which is why a straw appears broken in a glass of water. Absorption allows material to capture specific photon energies, heating them or re-emitting the energy as new wavelengths. In other words, color as we know it. Every color corresponds to a photon of a particular energy. Infrared light carries less energy than red light. Ultraviolet light carries more energy than violet. When sunlight passes through Earth's atmosphere, shorter wavelengths scatter more readily, painting our sky blue by day and crimson at sunset. This same scattering effect makes distant mountains appear hazy and gives thunderstorms their eerie greenish glow. Light's behavior in extreme conditions reveal even deeper mysteries. In the core of stars, photons generated by nuclear fusion undergo a random walk through dense plasma, taking thousands of years to escape. In fiber optic cables, photons zip through ultra-pure glass with minimal loss, enabling high-speed internet connections across continents. And in laboratory vacuums cooled to near absolute zero, researchers trap single photons in cavities, using them as carriers of information in nascent quantum computers. Einstein's theory of relativity shows that light is inextricably tied to time and space. From the perspective of a photon, if such a perspective could exist, time does not pass, and distances contract to zero. That means a beam of light from emission to absorption experiences its journey instantaneously and without length. While we cannot ride a photon, we can observe its effects: time dilation for high-speed particles, gravitational lensing of light around massive objects, and the redshift of distant galaxies as the universe expands. Light also underlies the technologies that define our era. Solar panels convert photons into electricity, powering homes and cities without greenhouse gas emissions. Medical imaging techniques from X-rays to fluorescence microscopy use specific wavelengths to peer inside the human body, diagnosing disease with precision. Lasers from barcode to scanners to fusion experiments exploit coherent light to cut, measure, and unlock the forces at the heart of the matter. From the simplest candle flame to the brightest quasar at the edge of the observable universe, light is both our messenger and our medium. It carries the story of atoms and galaxies, of time and space. Next time you witness a sunrise, remember that you are watching photons that were born in cosmic furnaces billions of years ago, and you are a part of the same luminous story. Thank you for watching. See you in the next video.